Hello friends, welcome to DCP, and this is the second problem in flexibility matrix or the forced method matrix, and this is total frame which has a deflection as well, and we need to find the reactions basically, and at the end we need to draw the bending moment diagram. So just to draw the bending moment diagram, we require the reactions at all the points as well as the internal reactions at the point B and C. By flexibility matrix, we get the reactions and then we can draw the bending moment diagram. If you have seen my previous video of flexibility matrix, it comprises of 5 steps basically. And the step 1 is to find the degree of static indeterminacy and marking the redundancy. So starting with the first step, the degree of static indeterminacy for a frame or for that matter any structure comprises of two parts, that is internal static indeterminacy and external. For internal, as you can see, this is an open frame that it does not have any loops. Thus the internal static indeterminacy for this frame is 0, and the external would be all the reactions, that is 3 here and 3 here, 6 minus the number of equilibrium conditions, that is 3. So capital R minus small r is the number of equilibrium conditions, summation fx, summation fi and summation m equal to 0. So 6 minus 3 is 3. Thus what does this ds suggest us is that it has three external reactions, three additional external reactions, due to which this structure has become indeterminate. If I just remove these three additional external reactions, my structure will become again determinate. Okay, so you can remove any three reactions, as we have 6 in total. I'll be removing all these three reactions, and thus my frame will become determinate again with a fixed end here. Alright, so the three reactions would be R1, R2 and R3. I've chosen the sign convention as upward positive and rightwards positive and clockwise positive. Okay, you can choose any sign convention. If you get the answer as negative, your directions will change. Second step is drawing the primary structure. Primary structure is the structure where we remove all the redundants that we had marked just now, R1, R2 and R3, and then we find the mx equation for all individual members. What are individual members? Wherever there is a point load or wherever a load starts or ends, for example a UDL, if it is not complete UDL, if it is only starting from year to year, at all the points you need to mark them. For example, here if here it was a point load, I marked it as E. Here it is a point load, I marked it as F. So the individual members would be AE, EB, BC, CF and FD. Fine. So we need to find the mx, that is just we need to find a moment at a distance of x. First we need to find the reactions here. Doing summation fx equal to 0, I get 26. Then summation fi equal to 0, I'll get 30. And summation ma equal to 0, I get the moment here as 185 anti-clockwise. Okay. To find the reactions or to find the mx equations, I just separate all these three members. Okay. Now we need to find mx for all individual members. So in this member, as you can see, there are two individual members, AE and EB. The first we need to find the reactions that are formed at end B. Whenever we separate a joint from a structure, there are three reactions that are formed there. Whenever we break a structure from any point, there are always three reactions formed. Okay, just like a fixed end moment, the vertical reaction, a horizontal reaction and a moment. So the vertical reaction to be calculated here would be 36, 36, and the moment of 95, it is 26 into 5. I'm taking the moment at B. 26 into 5 minus 20 into 2 minus 185. The answer I get is 95 kilonewton minus 95, which is basically saying that the beam is being rotated in an anti-clockwise manner due to all these loads and moments. And since here we need to write the reactive moments, then it has to be opposite of whatever you have got here. Okay, so if the beam was being rotated in anti-clockwise manner, the reactive moment would be formed in clockwise manner. Fine. 95 is the reactive clockwise moment. Now we need to find the mx for AE and EB as they are the individual members. I'll start taking a section at x from A. Okay, from A I have taken a distance of x and I need to find the mx here. The mx equation would be 26 into x minus 185. 26 into x going upwards, so it's a sagging minus 185 causing the beam to hog, so it is minus. Okay. For BE, I'll be taking a distance x from point B. Okay, from this point I'm taking the x, and the mx here would be minus 6x minus 95 because both the loads are causing hogging of the beam, right? Now, once we found these moments here, we need to translate them and change the directions like this. So if 30 was down here, 30 would be up here, as this joint is the same joint, B joint, right? So the overall summation of these reactions should be 0. These are all reactive moments and forces, and they should not cause any deformation. Hence, their contribution to any deformation or any rotation should be 0. Thus, this 30 is going to negate this 30, this 6 is going to cancel this 6, and this 95 is going to cancel this anti-clockwise 95. Okay, now whenever there occurs a load at any joint, I can take that load at at any member. When we separate the member, I can either take it here in this member, or I can take it here, but it is always better to take it on the later member. Okay, later means if this was AB, I'll take it on BC, on the next member basically. Now we need to find the reactions at point C. So the summation fx equal to 0, I get 10, 20, and yeah, there won't be any 20, and there won't be any vertical reaction. If you just calculate it, you can pause the video and calculate the reactions. There won't be any vertical reaction here. Fine. Now I need to find the mx equation for BC, and I'll be taking my section x starting from point C. Okay, the mx would be equal to minus 20 minus 6x square by 2 because of this UDL as well, right? Minus 20 minus 6x square by 2. Again, we need to translate these reactions at this point, but changing their direction just to cancel the effect of these reactions on one another. So this 10 cancels this 10, this 20 cancels this 20. So overall there is no force, external force on joint C, right? Now you need not find reactions at D because there is no support here. Okay, reactions are only found where there is support or where we have separated the member or separated the beam. So you need not find reactions at D. It is already balanced. If you see this 10 is going rightwards, this 10 is leftwards, they are balanced, and then 20 anti-clockwise, 10 into 2 clockwise, it is balanced again. Fine. Finding mx for df and fc. Now I'll take the section x starting from D for member df, and the mx for df would be 0 because there is no force acting from this side, right? So mx is 0. Again for member fc, I'll be taking x starting from D only because that is the finding mx. If I start my x from here, the mx equation would be easier. I could have also started my x from C, and then my mx equation would have been minus 20 plus 10x. Okay, but since I have taken x from D, my mx equation would be minus 10 into x minus 1, minus 10 into x minus 1, that is, this distance is basically x minus 1, right? So minus 10 into x minus 1 is your mx for fc. Step 3 is unit load structure. In this, you remove all loadings and apply unit load at redundance one by one, and then find mx for all members. Alright. So first of all, we have removed all the loadings here, and then starting from redundance one by one, that is starting from R1. If you recollect, your R1 was a vertical reaction, thus giving a 1 kilonewton in place of R1, and then finding mx for all members as we did previously. So first of all, let's find the reaction here. It would be 1 kilonewton downwards, and the moment would be 5 clockwise. Okay, again separating all the members and finding the mx equations. Starting with this member, let us find the reaction at point B. It would be 1 upwards and 5 anti-clockwise. For AE, again taking x from the same point, as we have taken earlier, you cannot change your x now. Alright, you have to take your x from A only. If you have taken in M0 equations, that is your previous equations, you have to take x from the same point in all the other equations as well. Okay, so taking x from here, I get mx equal to plus 5, right? Taking x from here, I get mx equal to plus 5 again. Translating these reactions on this point, I get 1 downwards and 5 up, clockwise. The reactions here would be 1 upwards and no moment, right? If you calculate, this is plus 5 and this is minus 1 into 5, that is 0. Taking x from here, I get mx equal to 1 into x, that is x. Translating this reaction here, and again taking x from point D, I get mx equal to 0. Again taking x from the same point for member FC, I get mx equal to 0. So I got the m1 equations. Earlier I got m0 equations. Okay. Now this was for redundant R1. Now we'll apply unit load for redundant R2. Redundant R2 was a horizontal reaction, and we apply a unit load in that horizontal redundant reaction. Finding the reactions here at point A, there will be a horizontal reaction of 1 kilonewton and a moment of 1 into the 2, right? This distance, perpendicular distance is 2, so 1 into 2, 2, and it would be anti-clockwise. Okay, I hope you know how to find these reactions. Like, this is very basic. Now we need to find the mx equation for all the members again. These would be m2 equations. Finding the reactions at this point again, 1 rightwards and 3 anti-clockwise. So mx for A, starting x from A, I get mx equal to x minus 2, and starting x from B for EB, I get mx equal to minus, okay, it's 3 minus x, right? Translating these reactions here, finding reactions here, I get 1 rightwards and 3 anti-clockwise. Taking x from point C, I get mx for BC as plus 3. Translating these reactions here, and now taking x from D for FD, I get mx equal to x, and again taking x from point D for FC, I get mx equal to plus 3. No, I'm sorry, it's x only, because we have taken like this, right? And x is from here, so 1 into x, that is plus x. Fine, these were m2 equations. Now finding m3 equations, that is applying the redundant at R3. R3 was a moment, right? A clockwise moment. So you need to apply a clockwise 1 kilonewton meter. Finding reaction at point A, it will be 1 kilonewton meter anti-clockwise. Separating all the members and finding the reaction at point B, I get 1 kilonewton meter clockwise. Taking x from point A and finding the mx for AE, mx would be minus 1, and taking x from point B and finding mx would be again minus 1. Translating this reaction here and finding the reaction at point C, I get the reaction as 1 kilonewton meter clockwise. Taking x from point C, I get mx is equal to minus 1. Translating this here, taking x from point D, I get mx equal to minus 1 again, and again taking x from point D for FC, I get mx equal to minus 1 again. Okay, so this is your m3 equations, right? Now you need to draw a big table. It is not possible for you to draw this whole table in one page, so what I suggest you is to draw it in parts. Okay, so you can draw this much table, that is still m3, on a single page, then the other table, half of this table on the below this table, and then the next half below that table. So in parts you can draw it, right? But for the sake of understanding, I have drawn it throughout. Let's start with the individual members, starting from this point: AE, EB, BC, CF, and FD. Okay. Now what is origin? Origin is that point from where you have started your x. Okay. So for member AE, you have started your x from point A. So the origin for AE would be A, origin for EB would be B, origin for BC would be C, origin for CF would be D, right? For CF you have started your x from D, and origin for FD would be D again, right? Now limits is basically how your x travels from A to E. For member AE, your limits would be how your x travels from A to E. So it starts from 0 and it has to travel 3-meter distance to cover up the whole entire AE, right? So it starts from 0 to 3. For BE, it starts from and it has to travel a distance of 2 meters to cover your BE. So it is 0 to 2. For member BC, it starts from C, that is 0, and it has to cover a distance of 5 meters to complete your BC, and thus it is 0 to 5. For member CF, right, CF, the X starts from here, right, 0, it has to cover a distance of 1 meter, but till 1 meter it was FD, right, it wasn't CF. CF starts from 1 meter and it goes till 3 meters, right? So the limits for member CF would be 1 to 3 because it starts from 1 meter and it goes till 3 meters. For member FD it would be it starts from 0 and it has to travel a distance of 1 meter, so it is 0 to 1. EI for the members as given in the question, it was 4 EI, 4 EI and 1 EI. M0 M0 equations, that whatever you got M0 equation for AE, it was 26x minus 185. For EB it is minus 6x minus 95. For BC it is minus 3x square minus 20. CF FD. M1 equation for AE 5 x 0 0. M2 equations x minus 2, 3 minus x, 3 x x, and this was I think all minus 1, right? All were minus 1. Okay. Now you need to find these terms delta 10, delta 20, delta 30, f11, f12 is equal to f21, f13 is equal to f31, f22, f23 is equal to f32 and f33. The formula for these equations is given as integration of a to b, that is from limits a to b. 10 is given as m1 m0, 20 is given as m2 m0, 30 is m3 m0, 1 is m1 m1, 12 m1 m2, 13 m1 m3, 22 m2 m2, 23 m2 m3, 33 m3 m3. Now you simply have to multiply it as it is, like m1 into m0 divided by the respective EI, that is 4. Okay, dividing it by 4 and putting the integration limits from 0 to 3. All these calculations have to be done on the calculator, and this is the most crucial step of solving a flexibility matrix. Okay, because most of the mistakes are done in this step only, so this has to be done very carefully, and even one mistake can lead you to a blunder. Okay, the whole sum would go wrong. Calculating all this in terms of EI, it takes a lot of time to calculate these, right? Okay, and finally you get delta 10, delta 20 and all these values by summing them up. So summing it up, I get it is equal to minus 979.687 by EI, minus 246.042 by EI, plus 236.25 by EI, 125 by 3 EI, 12.5 upon EI, minus 9.375 by EI, 139.6 EI, minus 8.875 upon EI, and 5.5 by EI. So these are your values that you need to require to put in the flexibility matrix equation. So this is your last step, that is finding redundant reaction values and drawing BMD. This is the flexibility matrix where n is the number of redundants, as in our case the number of redundants were 3, right? That is why we had to calculate the value of delta 10, delta 20, and delta 30, and this was, as this would have been 3 cross 1 matrix, this would be a 3 cross 3 matrix. Hence here you have to calculate F11 to F33. Here it would be 3 cross 1 again, R1, R2, R3, your redundants, and here this is delta dash 1, delta dash 2, 3 cross 1 matrix. And these values means that if there is any external deflection, if it is given in your question at any point of your redundant, then you need to put that deflection value here. Okay, but in our case there was no deflection given. I'll be solving one more sum in which there would be a deflection given, and we'll check the value of that sum as well, right? So putting the values here, delta 10, 20, 30, I get this big equation, and then solving this equation to find R1, R2, R3, I get your redundant values, right? So this is your R1, R2 minus 8.8788, and R3 is minus 20.513 kilonewton meter. These are your redundants, right? And once you have found these redundant reactions, you can easily find these three reactions, because now the frame has become determinate and it is easier to find these three reactions only. So finding them using the summation fx fy and summation m equal to 0, I get 8.446, 17.1212 and 38.9311 kilonewton meter. Now you need to draw the bending moment diagram and shear force diagram, right? But before that, before drawing the bending moment diagram, you again need to calculate all the reactions at every point, because you need those moments and reaction values to draw your shear force diagram and bending moment diagram. So finding the reaction values at point B, I get these values, translating them here, and finding the reaction values at point C, translating them here, and these are all your values. Okay, now let's draw the SFT and BMD. The shear force diagram for this would be 17.1212 upwards, then it would be constant till point E, then 17.1212 minus 20, I get around 2.8788 downwards, then again constant till here, and this is your SFT. Your BMD would be 38.9311 downwards, then 17.1212 into 3 meters. I am finding the BMD at point E. 17.1212 into 3 minus 38.9311, I get 12.42, right? And then 6.6749 joining it. So this is your BMD for member AB. SFD for member BC would be 8.446 upwards, and then joining it down, that is 8.446 minus 6 into 5, I get 21.554 downward shear force diagram, and then joining it. This is your shear force diagram, and this suggests that here it would be maximum, right? So you will have to find the maximum moment at this point as well. 6.6749 upwards, then 26.0951 here downwards, and you just need to join it parabolically. This is your BMD, but the maximum value is occurring here. So for that you'll have to find this distance using the similar triangles. So this distance is given as 1.40766 meters, right? And finding the moment at this distance, that is 8.446 into 1.40766 plus 6.6749 minus 6 into 1.40766 square by 2, I get this maximum value. So this is your BMD. And for the last member for this diagram, 18.8788 upwards, then it will be constant till F. 18.8788 minus 10, that is 8.8788, then constant till this point, and again 0. The bending moment diagram would be 26.0951 minus, that is here downwards. At point F it would be 18.8788 into 2 minus 26.0951, it will be 11.65, and then here it will be 20.5413 joining it. This is your bending moment diagram for CD, and this completes your sum. using flexibility or forced method, and I hope it was fruitful to you. Please support this channel. Please like, share and subscribe as much as you can, and stay tuned for the next video. Thank you so much.